Yeah, we have Daniel Waldram telling us about our geometry. Thank you very much.
Thank you to the excellent organisers for inviting me. Great meeting, very, very smooth. So I also wasn't quite sure how to judge the talk, so I'm going to tell you some things. Some of it will be a bit introductory, and I apologise to those who know that. And then at the end, I'll try and get a little bit more less introductory, and I'll end up talking about a lot of analogies rather than telling you the details. I hope that's okay. So, okay, so what am I going to tell you about? So, I think you know that supersymmetric backgrounds are kind of ubiquitous in string theory, right? So you care about them because you might want to build a particle physics model. You might want to take 10 on that dimensions and compact it by down to 4 or build some particle physics. You might want to do ADS-CFT, right? So my motivation, so I'm going to give you a little bit of introduction to start with. So the motivation, so a couple of things you might want to do. You might want to do particle physics. So this is such an old subject. So I might want to take my manifold to be, so my space-time might be something like flat space times some internal manifold, and that might be 7-dimensional if we're in M theory, or it might be 6-dimensional if we're in type 2. Or I might want to do ADS-TFT. And then I might have some ADS by times some manifold. Again, it could be an M theory. And typically what we do, right, we treat these things to be supersymmetric, and then you break supersymmetry in the standard model or something in the supersymmetric standard model, or here you typically have supersymmetry. So we're interested in how you can construct solutions like this. And what you're used to is that what we know how to do is to construct them typically when there are no fluxes turned on, right? So if you remember about the supergravity, so here's supergravity, it's gravity plus some fluxes. And depending which supergravity you do, you get different kinds of fluxes. What do I mean by flux? I just mean some p-form field which has got some p-1 form potential. So typically you might do a compactification here where this is Calabi-Yau or something, right? What's much harder to do is to do a supersymmetric compactification, which is something generically supersymmetric that's got fluxes turned on as well. Similarly here, we know lots of examples, so this might be a Sasaki-Einstein space or something, I do an equal one. But there's lots of other backgrounds that would have fluxes turned on that we don't really know how to think about this. And we have some nice mathematics for these spaces. So, you know, Calabi-Yau manifolds, we have theorems about when they exist, for example. We don't have any nice theorems when there's fluxes turned on. So what I'm going to do is to tell you about a geometry about how you understand these backgrounds when the fluxes are turned on. And it puts it in a language which is very like the kind of classical language of geometry. And that's interesting because it means that you can calculate some things you wouldn't otherwise know how to calculate. And it also suggests that there may be theorems that are like the Calabi-Yau theorem, which are existence theorems, which would be great. So that's where I'm going. So, let's see, so, yeah, so I'll do it in 2 parts. So I'll start by telling you how to do supergravity without trying. So that's going to tell you how these geometrical structures sort of naturally exist. And then I'm going to talk about moduli. So I'm going to talk about how to calculate moduli. So what do I mean by that? So I think you probably know. So a modulus here is where I deform the geometry and doesn't cost me any energy. Okay, so if I had a torus, for example, I could just make the torus a bit bigger, it doesn't cost me any energy. Moduli and ADS-CFT, again, it doesn't cost me any energy, so it's still an ADS solution. So an ADS-CFT in the dual field theory, that's what's a marginal exactly marginal deformation. It means I can deform the theory, it remains conformal. So if I can calculate moduli, from this point of view, they correspond to massless scalar fields. And here they're going to correspond to exactly marginal deformations. And in this, so in both cases we're interested, we'd like to know what the exactly marginal deformations are, we'd like to see what geometries we get. Here, massless scalar fields are bad for particle physics. And I'm going to say something I don't really understand. After inflation, you have reheating and it goes into mass scale fields, and that's bad. I think those are the words I'm supposed to say. So typically you want to stabilize these things, and traditionally people have stabilized the moduli, so in this case you can stabilize moduli. That's a long-standing question, how you give masses to them. And one way you can give masses to them is turn on a small flux. So that's where the flux is very much smaller than the inverse Kaluza-Klein scale of this manifold. So there's a natural scale to the manifold, right? The fluxes are dimensionful. If they're much smaller in mass scale than the mass scale of the manifold, I can think of it as a Calabi-Yau with just a tiny bit of flux turned on. If I think about the equations of motion, I've got some Ricci tensor, which is going to look something like the flux squared. And so to second order, to first order, this is just 0. So when I turn on this to first order, it doesn't really change the geometry. But what it does do is it gives a little bit of, it does correct whether things are moduli or anymore. Because you can have, if you imagine having a torus, and you've got some flux on the torus, if I enlarge the torus, right, that's going to cost me energy because I have to deform the flux at the same time. So in general, by turning on the fluxes, you can lift some of these moduli. And the way people have done it in the past, they've always calculated it in a small flux limit. So one thing I'm going to do is to tell you how to calculate it exactly. That's a new calculation people didn't know how to do. Okay. But this geometry will allow you to do that. Okay, so is my motivation kind of clear? I should have said interrupt me as much as you want. The people who I taught MSc to all right, so let me tell you how to do start by telling you how to do the geometry. So all I'm going to do to start with is say, suppose we have some flux. So let's just take a minimal thing. You've got some, all we're going to say is that we know we've got a field which has some flux. So I'm going to tell you now how to, I'm going to talk about diffeos and gauge transformations. Okay, so suppose I've got some flux with some potential. And suppose I think about my symmetries. Well, in general, I can change the gauge potential by doing a diffeomorphism. Then I take the Lie derivative. Or I can do a gauge transformation. Okay, so I take the derivative of something. So this is some p form, some p minus 1 form, some p minus 2 form. Okay, so now you can ask yourselves, what happens if we do an algebra, right? So there's going to be some algebra of these things. So when I do 2 of those, it better correspond to something, another transformation. So what do I get? Well, the psi prime here, I think you know how to do that. If I do 2 diffeomorphisms, I get a diffeomorphism that's just the Lie bracket between the other 2. Okay. If I do the gauge transformations, well, it just depends on D. So I can fix D of this thing, and I find that it's given by something like the Lie derivative of D of this one minus the Lie derivative of D of this one. But I'd really like to integrate this back to an actual lambda. So what do I do with lambda? So can we integrate? And what you find is you can't, obviously there's lots of choices you can make, but you find that you're stuck, so you can't get a Lie algebra. So you find that either you violate, either the bracket is not anti-symmetric, or you find that you don't satisfy Jacobi. So I can think of all the different ways I could integrate that up to things that are exact, right? And I find that there's none of them I can do so that actually when I define these 2 things, it's just an ordinary Lie. I can think of it as just some bracket between these 2 things that's anti-symmetric and satisfies Jacobi. To a mathematician, what this gives you, so if I have psi double prime as bracket, and I have some lambda double prime as something. Let me just say something there for the moment. This gives what a mathematician would call a Lie algebra, it's called an algebroid. So it's some kind of thing. Okay, just some gadget. Okay, is there anything more we can do? Is there anything that might tell us how to do this integration? So we could look at a special case. So let's look at the special case where we just had a freeform. So f is just a freeform. So in that case, lambda is going to be a one form. And it turns out that there's a sort of natural contraction I can make. So if I think about psi plus lambda, this is now an element of it's a vector and a one form. Right, so I'm just sort of putting them together into a single object. Let me call this something. I'll call this thing E, and I'll call it the generalized tangent space. Okay. It's like a tangent space that's twice as big. Now, on the generalized tangent space, I actually have a natural metric, which I'll call eta, which I can construct just by contracting the vector and the one form. Is everyone okay with this notation? Just maybe in a contraction of those two things. Or if you like, I can think of that as vector. And then here I put 0, 1, 1, 0. Right, just doing that thing. So there's a natural metric that's off diagonal like that. What kind of signature is that? Well, that's an ODD metric if this is in D dimensions. These are like null directions. I've got D null directions. That's like I've got. So on this space, if I just took the case where I took three forms, so this is a one form, I have this natural metric. And then I can do something interesting. I can choose my integration in a particular way. So I can choose. So I can take again, I take psi double prime to just be the bracket, and I'll choose lambda double prime to be the following thing. So it's the Lie derivative there, and then I take contraction there. So you can see it's not symmetric, not anti-symmetric. Okay. So I can think of this as defining a bracket. So together these two things define a bracket. So if I have psi plus lambda, psi prime, plus lambda prime, this bracket is given by, sorry, I don't know why I'm writing out here. Okay. Defining this new bracket on these things which are living in these are generalized vectors. Now what's remarkable is that this preserves the ODD metric. So what do I mean by that? I mean that if I take this eta and take UV, W plus eta V U. This is just the same thing as the Lie derivative, pi u of eta EW, where pi u is the vector part. So now U, V, and W are all generalized vectors. So this is like Leibniz, right? I'm kind of acting with an operator here, it just hits this operator, then it hits this operator, and it doesn't do anything to eta. So eta is invariant. Yeah?
Sorry, can I ask, if lambda prime prime is not anti-symmetric anymore,
Yeah.
then when you take this delta transformation,
Yeah.
what does d lambda prime prime mean? Because you don't have p minus 1 form.
Right, so although this is not anti-symmetric, if I take d of this guy, it is anti-symmetric.
Oh,
So if I think about the algebra of just the symmetries, everything is still nicely algebra. It's when I'm trying to go back to write it as a, that's a good question, when I'm trying to go right back to write it as a one-form lambda, then I can't make it out of symmetry. Okay. Other questions? Okay. So before we had this kind of general algebroid, this thing defines a special kind of algebroid. So there's a sort of special algebroid on P, which is T plus T star, which preserves this ODD structure. And it's this second bit which is going to be really useful for us. Okay. So now actually you can think of, now you can think of this thing, right? You can think of this bracket. That's sort of the analog of the Lie bracket. I could equally well think of it as a kind of generalized Lie derivative acting on a vector. You know, like the Lie derivative when you act on vectors is like a bracket. So I can define a kind of generalized Lie derivative. And now actually, because of this structure, I can think of this guy acting on any ODD representation. Because it preserves the ODD structure, I can think of things, this formed a kind of ODD representation, it's like the vector representation. But I could take some other ODD representation that's going to be built out of tensors. And now I'm going to be able to define a sort of generalized Lie derivative acting on it. So in particular, I could take the spinor representations. So there are two spinor representations of ODD. And what do they look like? Well, it turns out that if you work out, here we took the vector representation and decomposed it into regular tensors. It was a vector in a one form. I can take the spinor representation and decompose them, and what do I get? Okay, I get something slightly funny. I get this determinant bundle, that's just like a top form, that's another way of saying that, but I'm taking it to the half power, so I'm assuming things are orientable if you care. And then I get either odd or even forms. So those are called polyforms usually, so sums of odd or even forms, so I mean like 0, 2, 4, 6, or 1, 3, right, like combinations of them. They correspond to spinors. And now I'm going to do a little kind of slightly painful little thing, but it's actually what we need to do. There's this funny determinant bundle here, right? That's a bit painful. We'd like to get around it. So actually, let's think about a slightly larger group. I'm going to go from ODD, and I'm going to promote it to ODD times some sort of rescaling. And this rescaling is going to just be the, it's going to be like a weight. So it's going to be a weight of a determinant bundle. So all I'm doing, I'm allowing myself some extra bit of scaling. So now when I have representations, I need to think of them as representations of this, and they're going to have some weight under a determinant bundle. So then if I take what that allows me to define things that have weight a half, right, and there, so it should be minus a half. And that will exact these things, because of the weight a half, it will cancel this, and these will be honestly sums of odd or even. So all I want to say is that when you do this, it's kind of natural to introduce this R plus scaling as well, because it allows you to have more sensible representations. Has what I've said made sense? Okay. So that's the setup. And this is what we call ODD times R plus generalized geometry. Right? It's just this differential geometry. It's kind of silly, right? It's just ordinary differential geometry kind of promoted in some way. To a mathematician, it's some exact Courant algebroid. That's not worried. Okay, so we set up that kind of geometry. So now what would we like to do with it?
So
Yeah.
A little question.
Good.
At the very start, when you wrote down what the action of the Lie derivative and gauge transformation was, you only wrote a small gauge transformation.
Yes.
Do things change in any way when you consider large gauge transformations instead?
That is a whole interesting question. Absolutely. I also kind of ignored anything to do with like quantization of the flux, which might put you into something where those gauge transformations are not quite as general as you might think. You might want to think about a gerb or something. So yeah, that's a whole interesting question, which I'll just kind of. All right. So what do I want to do with it? Well, what I'm going to do is I'm just going to do Riemannian geometry, but now in this slightly bigger picture. So, it's too much. So let's do generalized Riemannian geometry. So what do I want to do? So first of all, so what do we do for Riemannian geometry? Well, we need to define, first of all, we need to define the Ricci-Vita connection. The usual object, right? We've got a metric, we want a connection, and the derivative of the metric vanishes and is torsion free. So can we do the same thing? Let's see if we can do the same thing. So we need to start by introducing, so we need some generalized connection. So how might we define that? So we've got some kind of Vm, I'm going to write it with an index now, which is like Vm lambda m. So the big M is running from 1 to 2D, that's my generalized vector. And I want to take the derivative of it, right? So I might want to map this into something which is dm Vm. And the first bit better look like an ordinary derivative, so let me just write that. And then I'm going to have some kind of connection piece, something like that. So what do I mean about these two bits? This derivative is in 2D directions. So in general, I can take derivatives along vectors and along one-forms. So what I really mean here is that I do nothing along the one-form, and I just take the ordinary derivative, partial derivative along the other. Right? That's what I mean by that. This bit, well, it's essentially something that looks like E star, because it's got this index. And then it wants to transform. In general, it could be a general linear transformation. But remember, I had this structure, which was ODD times R plus. So I might as well actually just put it in the Lie algebra of ODD plus R. So it's going to still preserve that metric. This is not just the ordinary connection that's taking values in this. It's bigger because this n index is running over all 2D directions. Okay. What's remarkable is I can still define torsion. So you can still define a notion of torsion. And that's not straightforward that you can do that, but it turns out you can. All right, so now I'm just going to do analogs. So what do we do? So let's start with the structure group. So in ordinary geometry, right, all your tensors are representations of GLD. And let me think of this in a sort of silly way. I'll think of this as R plus. Maybe I'll keep some orientation, so think of it like that, right? Just for analogy. So now my structure group is going to be this ODD times R plus. We have a tangent space. So here was just the ordinary tangent space of the manifold. Here it's these generalized tangent vectors. And then we would have a metric, G. And this would be invariant under OD. Now, OD is the maximally compact subgroup of this group. Okay. So let's do the same thing. Let's define a generalized metric, which which is now going to be invariant under, and what's the maximally compact subgroup of this one? It's OD times OD. So let me just choose to do that. Okay, and then we have Levi-Civita, which should say that the derivative of the metric is 0, and the torsion is 0. So now I can do exactly the same thing. I take that the generalized derivative is 0, and that this generalized torsion is 0. Okay. So you can do that, interestingly. And you can keep going. And you can define Ricci tensors. So here we just got the ordinary Ricci tensor. And then here I've got some generalized Ricci tensor. And something interesting or maybe remarkable happens. So first of all, you find, well, you ask, what does G look like? And G can always be written in the following way. Remember here we've got F is TA, A is twofold. This probably looks familiar to you if you know about toroidal reductions. And then you can write down an action, which is just, it turns out that this generalized metric defines a natural volume form that's invariant on the ODD. And then you just stick here the generalized Ricci tensor, and you work it out, and what do you get? You get this action. It's just supposed to be just the Ricci scalar. And this action is the action of type 1, or if you like, type 2, the Never-Schwarz sector of type 2 supergravity. So all we put in was this kind of ODD structure group, and then we just turn the handle of doing Riemannian geometry, and we get out supergravity without ever mentioning fermions anywhere. Slightly bizarre, but that's what happens. Right, this is usually, we usually call, F is usually called H. It's the 3. And here's called B. Okay, so just a couple of comments. Okay. And then just to say the equations of motion are just that the generalized Ricci tensor vanishes. So from that point of view, the equations of motion, this is a pure gravity theory, right? It's like a pure generalized gravity theory. It's just Ricci flat. So we kind of geometrized the dilaton and the B field into this bigger object, and everything is really just Riemannian geometry, but in this bigger language. Okay. You make a couple of comments.
Sorry, just to make sure I understand, the
first
integral here we have in the action is integral over your generalized manifold, and the second one is integral over M itself?
Right, good. Excellent. So I'm always working just on a regular manifold, but I look at a tangent space which is sort of Tm plus T star M. So I'm doubling the tangent space, but the manifold remains the same dimension.
Okay.
That's an excellent question. Because there's also something called double field theory, which you've probably heard about. And there people try and double the size of the manifold as well. Okay, I'm going to now step over here. That's a hard thing to do because it's not always clear that you can double the manifold in a sensible way, that you can define all the structures. Okay. It's an interesting thing to do.
Are there any obstructions being able to put this onto the manifold other than the word those that would go into defining that kind of constituent object?
No. So this always, you can do this on any manifold. I've secretly assumed orientation,
Okay.
but I can even get away from that if I want to. Yeah. Yeah, go on, please.
were you about to answer more of the question?
I was going to go off on a tangent, so it's probably a good thing that you asked me another question.
I was just wondering if this necessarily dissents from string theory somehow, or can you just do this just using geometry? Like, would you universally expect string or M theory to be the UPV completion of this kind of thing?
So I think that's a really interesting question. Let me just postpone it for a bit and I'll come back to it. As stands, I just constructed it geometrically and all. Didn't even put the fermions in. So just some comments. So you can do this with a full D equals 10 theory. And then really what I need to take is 091 times 019 side 01010 times R plus, right? Because I want to get Minkowski signatures. But I can do that, that's fine. Or I can do it for the theory restricted to D Euclidean space, right? So then I would do the ODD theory. So what I mean is I could take this theory, which strictly lives in 10 dimensions, I could just focus on a Euclidean space at dimension 6 or something, just release that. You can also add in the Ramon-Ramon fields if you want. And they transform in these spinor bundles. So I can include the Ramon-Ramon fields in the type 2. And I can also do the fermions. And they transform under the spin D times spin D. So, you know, in type 2, there's 2 fermions. Everything comes in pairs. And they transform naturally under these 2 spin groups. Okay. So now to come a bit to your question. So let me just point out a pattern now. Because I want to do one more thing. So let's look at the pattern. So let's think about simply laced the algebras. So there's the A series, and for any given Lie algebra, right, you can have different real forms. And there's always something called the split real form, which is the one that sort of maximally has positive and negative directions. Yeah. So the split real form here, you might think this was SU D minus 1, SUD. The split real form is SLDR. And let me put in an R plus factor. So then what's the other simply laced, right? So you could do the D series. And that has a split real form that's SOD D times R plus. That was the one we just did. So this is just conventional Riemannian. This is just conventional geometry. Right, if I went through that, I'd just get on Riemann theory. This one was like the, this one was sort of the Never-Schwarz sector. And we went through this theory. So there's an obvious thing to do, which is to do the E series. And the split real form there is written as EDD. This tells you about the signature of it. That's that D in brackets. So again, I do it times an R plus. And what happens when I, so we do all those things, and they all actually work the same way. So they each come with a pairing. So, which takes 2 generalized vectors, symmetric generalized vectors, and maps me into some other representation. I'll tell you what that's going to be. So for the SLD case, this n bundle is just, it's not there, it's 0. And the pairing is just, there is no pairing. There's no way to take vectors and pair them together, right, in some covariant way. For the ODD case, this is just real numbers. And the pairing was the one that we looked at, which was just this ODD metric. When I do the ED case, there's again a pairing, and if you know your representations, if you know your fundamental representations, the E bundle corresponds to that node of the thinking node, and N corresponds to that node of the thinking node. So there's again a pairing, but this is now not real numbers, it's just some number. And you can then turn the handle, and what happens here is like so. In this case, the exceptional, there are two possibilities. So one of them looks like Tm plus wedge 2 T star m plus wedge 5 T star m plus some weird thing which looks like Tm tensor wedge 7 T star m. And the other one looks like Tm plus 2 copies of T star m plus wedge 3 T star m plus 2 copies of wedge 5 T star m plus some weird thing that looks like T star m tensor wedge 6 T star m. And this works, you can do the generalized geometry for all d less than or equal to 7. And here, the dimension of the manifold is equal to d, and here you have to take the dimension of the manifold to equal d minus 1, so these two m's are not the same. You turn the handle, and if you work out this thing, you get two possibilities. You either get M theory on M, or you get type 2B on M. So if I take this bundle, I get the type 2B. If I do this one, I get M theory. What I mean is the 11-dimensional supergravity reduced to a 7, 6, 5 dimensional manifold, or type 2 supergravity, type 2B supergravity restricted. So it completely geometrizes all the fluxes, that's what I'm trying to say. And if you want to understand these bundles, right, these are diffeomorphisms, these are gauge transformations that come from the fact that there are membranes in the theory, that's why there's a 2D. These are gauge transformations that come from the fact that there are fibranes in the theory. These are really the Kaluza-Klein monopole duals of these diffeomorphism transformations. Okay, so what I'm trying to say is, like, you can always construct, if you take the E series, you can turn the handle in the same way. When you do it, you get the fully geometrized graph. So to your question, you might ask, is this something that's sort of necessary in order to write down a quantum theory of gravity? That's a very, very broad question. I don't think I have an answer for you. But you might wonder whether the ingredients, so what are the minimal ingredients? It seems like we have these two spaces, and we have this pairing, which takes this to this. And then what happens is that the structure group, the structure group, is equal to the invariance group of the pairing. So in this case, it was obvious. This was just the ODG metric. The thing that leaves that metric invariant was ODD. So you didn't need to know OD, you just had to have the pairing. Here, if you have the map from here to here, you can again show that that's invariant under the E group. So, and then once you've done that, it's then constructive. So then it's then just a construction, which gives you Riemannian geometry, the generalized Riemannian geometry. So you might wonder whether somehow this structure is somehow inherent to things which have nice UV completions. I have no reason to believe that's true, except that, let's look over here. If you look at string field theory, closed string field theory, it has a little bit of this kind of structure. Okay. That's the first bit of what I was going to say. Do you want to ask me questions? Yeah.
for example, have a notion of Hodge star with these generalized metrics?
So you have, yeah, so what's going on there, really, the Hodge star, right? It's saying that if I have the metric, then all my tensor representations decompose into OD representations. And if I have two representations that are equivalent, I have a map between them, which is the Hodge star. So the same thing happens here. So you have the maximally compact subgroups. So here it's OD times OD. Here it's some group HD, which depends on what the group is here. And I can always decompose things into this. Once I've got the generalized metric, I can decompose things into this. And then I may have relations between representations like the Hodge star.
So it's like pairing V star W's volume form kind of stuff.
You can have things like that.
Okay, cool. And so is the Ricci scalar also just constructed in the obvious way, the vol GR?
Yeah, so, okay, I glossed over a little bit here. So constructing that guy is kind of interesting. So the vol G term I can just basically get from the generalized metric, is defined by the generalized metric. This term, I had this generalized connection, right? So you think you would just go ahead and calculate the Riemann tensor, and then like, two interesting things happened. The first one is that this is not unique. That's totally, I should have told you that, right? I hit it. Levi-Civita, you solve those equations and you get a unique connection. Generalized geometry, you solve those connections, it's not unique. Now that's not weird, that's not totally weird. Other geometries, that happens all the time. If you have a complex structure and you want a connection that's compatible with the complex structure and tuition-free, it may not be unique. So that's very typical. What is remarkable is that if you construct the Ricci tensors, you get the same answer independent of which choice you make here. So these guys are unique. There's also a question about whether you can construct Riemann. And roughly, because the bracket is not antisymmetric, the naive thing you write down for the Riemann tensor will not be a tensor. So constructing Riemann tensors is an interesting and difficult problem. In the ODD case, we know how to do it. In this case, there's actually arguments you can't construct the unwanted Riemann tensor. Any other questions?
What does the condition of having a simple algebra and doesn't construction? Like, can you do it for other groups?
Yeah, so it's just sort of interesting that there's three families for simply glazed that give you the supergravities.
Okay.
You can ask in general, if I have these pairs, what kind of groups can I get? There's not a complete classification, we know certain examples. Typically, you can certainly do SO D plus N, this gives you some kind of heterotic theory. That's also possible. Symplectic groups seem not to work in a natural way. You can sometimes change the representation here. So there's a sort of story, you can do different things. I don't know any examples that don't somehow live in supergravities one way or another. There might be some.
So you, at the end of the day, you get supergravity.
So far, it seems like you get supergravities. Any other questions? All right, so I guess I have 10 minutes. Okay, so let me, so what I was going to talk about now is the moduli problem. So I'm not going to tell you how to do the moduli problem, I'm just going to give you lots of analogies. So let's start by just thinking about supersymmetric backgrounds. So far I told you how to construct supergravity. Right? What do I mean by supersymmetric background? Typically what I mean is, so let's do something very concrete. Let's do type 2 on R31 times M. So this is what I might want to do if I was doing phenomenology. Compactify down 4 dimensions. Preserve some supersymmetry. So when you preserve some supersymmetry, you have to satisfy what's called the killing spinor equation. And that basically comes from saying, like, okay, we're in type 2, so we've got a pair of Gravitini. We want the Gravitini, their variation looks like some derivative of some spinor parameter plus some flux with the spinor parameter. And to preserve some supersymmetry, we need to set this to 0. We have a bosonic background that satisfies that as 0 for some epsilon. So if I set the flux to 0, then I just have this equation. And I have a solution where I take them both to be the same spinner, eta. And I have a single spinner, and this gives me the Calabi-Yau. This is the Calabi-Yau diagram. So Calabi-Yau is a manifold that emits a solution to this equation for a single spinner. And if you think about it, well, the spinner will be spin 6, because this is a 6-dimensional space. That's the same as SU4. So I'm picking out a single spinner, so it's going to have some component there and then zeros. Right? I'll pick out one spinner. So the spinner is invariant under the group SU3. So that's the reason Calabi-Yaus have SU3 autonomy. Or equivalently to a mathematician might say it has SU3 structure. It means that when you twist the tangent space, you can only twist it by SU3. Otherwise, this guy wouldn't exist. Now, there's an equivalent way of thinking about that. I can think of it as defined by a pair of objects, a 2 form, a symplectic 2 form, and a holomorphic 3 form. Maybe you've seen that before for Calabi-Yaus, I don't know if you have. And what's going on here is if I have a GL6 group, if I have this symplectic 2 form, this 2 form, they have to satisfy some particular algebraic conditions that I'm not writing down. This holomorphic 3 form preserves an SU3 group, SU3C group, and the common subgroup is SU3. So I can think of this structure as being defined either by a metric and a spinner, or I can think of it as defined by these 2 objects, these 2 invariant objects. Is that okay? Ish? Okay. So, if you have this condition, these guys have the extra property that they're closed. And that's actually, there's an equivalent way of thinking about that, which is there exists a connection, it's like Levi-Civita, such that the derivatives of these things are 0 and the torsion is 0. Now, in general, you can't find a connection like that. Only if they're closed can you find such a connection. This is what a mathematician would be called a torsion-free SU3 structure. And the nice thing about thinking about it that way is you can do it for all sorts of geometries. So if you're used to G2 harmony geometries, again, the conditions are that you have a torsion-free G2 structure. If you have an integrable complex structure, it's a torsion-free GL D/2C structure. If you have a volume form, it's a torsion-free SL. Right? So any geometry you want, you can think of in that language. And if I want to do the moduli, well, let's really cheat. I'm going to cheat. This is not the way you do the calculation. But I do a variation of these guys. I still want them to be closed. But I want to do it up to diffeomorphisms. So what's a diffeomorphism? That's the Lie derivative of this guy. This is closed, so the Lie derivative is actually just d of the contraction. And similarly, the Lie derivative of this guy is also just d of the contraction. So I'm doing closed things up to exact things. So the moduli are going to be counted by h2 of the Duran, that's for the omega, and h3 of the Duran complexified, that's for that big omega. Okay, strictly if I rescale this omega, it doesn't change the metric. So actually it's got one less degree of freedom. And also this is a bit of a cheat because you have to work a bit harder. This is not really, right? There's only one parameter psi here, but that's the idea. Okay. So now I'm going to do a general flux background. So that was without flux. Let's do it with flux. And what happens is now, okay, so I have to do some packaging. I put the two spinners together into a bigger object. This is SU4, this is SU4. These two things go together as SU8, which is just this H7. That's the maximally compact subgroup of E77. Which is kind of what happened. That was the way it had to work. Just believe me on the way the groups work. And the variation of the Gravitino now is something which looks like D of this thing, but that is that Levi-Civitali connection. So again, I've geometrized all the fluxes. So now if you want a supersymmetric background, you need some single spinner, which is now going to look something like 0, 0. So that's going to define some SU7 structure inside SU8. So now in the generalized language, a supersymmetric background, and now I'm allowing the fluxes to turn on, is an SU7 structure. I told you for Calladiaus there were some objects that were equivalent to defining the spinner. This thing turns out to be equivalent to defining something we'll call psi, which transforms to the, wait for it, the 912-dimensional representation of E7. This is some collection of forms and tensors. Don't worry. And Suzy corresponds to a torsion-free, generalized SU7 structure. And this works in general. If I have more supersymmetries, other dimensions, it's always a torsion-free structure. So it puts it in the same language. Okay, and then in the last 1 minute, this thing actually translates into two terms, one of which looks like a superpotential. So it looks something like some variation of a superpotential with respect to this field psi is 0. This field psi is a field, so it's the space of psi is some infinite dimensional space. So this is really a superpotential on an infinite dimensional space, but it's still a superpotential. Do you know N equal 1 language? And the other term looks like a D term. That's a moment map. It turns out if you want to calculate the moduli, you basically just need to use this bit, and this is some sort of holomorphic data. So I'm glossing over a million things. Here the moduli were counted by some cohomology. The same thing happens here. It's calculated by some cohomology that's defined using this D operator. It's not less like the Durand cohomology, it's more like the de Bow cohomology because there's some structure. But in general, the moduli correspond to cohomology. And not only that, you can calculate what this cohomology is. So in general, you have to use something called a spectral sequence, which is a thing in geometry. This operator decomposes into a bit that looks like de Bow plus a bit that depends on the flux. You get a double complex, and from that you can calculate what it is. You do the calculation, and you find that the calculation people did with the small flux approximation actually works to all orders. It's true. So that's good. And in the last -1 minute, I will tell you that you can ask something else, which in a sense is more important, which is, what about string corrections? So the actual string action, right, is like supergravity. And then at higher order, there's going to be terms that look like r to the 4th, and there's going to be higher order terms that come from string corrections. When you look at the string corrections, you may know about, in N equal 1 theories, there are non-renormalization theorems for the superpotential. Something like that, you can use an argument that this guy does not change by perturbative corrections. So in fact, the calculation of the moduli works is still true for all perturbative corrections to string. It's going to be broken by non-perturbative corrections because then this thing becomes not local. but this same argument should go through. And then you can use similar arguments to calculate the marginal deformations of field theories. There's a whole story of stuff which I should talk about. So I'll stop there.
Thank you very much. Questions, anyone?
Thank you for excellent talk. Do you mention how you can define a moduli of this sort of space by cohomology groups?
Yeah.
Is there any connection you think we can relate to like twistor theory? A lot of twistor theory is based in like cohomology.
Yeah, I understand. I haven't thought about it, but they could be. So in twistor theory, there's a sort of standard twistor theory that's the one that was first written down as sort of relevant to that's relevant to Poincare symmetry. But there's a generalization of twistor theory that can use other groups, and it's to do with looking at certain parabolic subgroups in other groups. And so I could imagine that by thinking about some of these other groups, we might be able to connect it to twistor theory that way, twistor transforms, but I haven't thought about it. Yeah.
Maybe you said this, but I missed it. Is the cohomology you're talking about, is this integral or real?
It's just the real cohomology.
Okay. Do you know if there might be any relevant physical information in the torsion part that you are blind from?
That's interesting. Yeah. So okay, good. So there's a couple of things that I glossed, many things I glossed over. But one of the things I glossed over is like, probably the best way to say that you could ask for things like, can I also understand brains living in this background?
Okay.
Right? And we know that brains strictly are some K-theory classes or something, but more generally they're kind of like, they're more like related to integer cohomologies.
Okay.
So I think that would be the most natural thing, that they're going to be related to if you have some flux around, if you want to look at brains in the background.
Thank you.
Yeah.
In the M-theory setting, does the same thing happen where you can use this argument to
For the
learn
corrections?
something about the correct, like aren't just the first three corrections protected in M-theory?
Yes, so, no, that's absolutely right. So yeah, this argument goes through either 2B or M-theory, and I'm not saying, I'm being completely agnostic, so it's not that the terms are protected by supersymmetry. What I'm doing really is taking the M-theory and rewriting it as though it was a D equals 4, N equal 1 theory with an infinite number of fields. So I've sort of like taken all the Kaluza-Klein modes and think of them as chiral fields. And the good thing is that this thing you can go off shell. So I go off shell in that theory because we have a formulation of that with auxiliary fields. So I go off shell in that theory, and then I just actually, it's not really a non-renormalization theorem, it's really just writing down what are all the possible superpotential terms you could write down that are compatible with the supersymmetry, the off-shell supersymmetry. And you find there's only one. So I think it says that whatever the corrections are, we just assume diffeomorphism invariance and the gauge symmetry of the fluxes, that this cannot get corrected. So it's not so much that there are terms here that are not that are protected by supersymmetry, it's more just an argument about what you could possibly write. Yeah.
In the P equals 1 case for your gauge fields,
Yeah.
can you think of these connections as like a horizontal distribution on your E bundle? You know, like how you have your gauge field?
If you want to do the ODD case.
Yeah, sure.
Yeah. No, not really. No, it doesn't have that picture. It doesn't have that picture. Yeah.
Is this cohomology that you alluded to, is this just equivariant cohomology? Because you mentioned the moment map and this can be used offline.
Yeah, good. So yes and no. So the answer, the no is this moment map is sort of not a moment map on the manifold itself, but it's a moment map on this infinite dimensional space of structures.
Okay.
And I should have said that these kind of equations put it very much in the language of what's called to mathematicians the Kobayashi-Hitchin correspondence. which is a connection between solving differential equations and thinking of kind of algebraic geometry, so sort of infinite dimensional algebraic geometry. So it's not a moment map on the manifold itself, so that means it's not equivariant. But there's something very interesting that happens is that if you do this for the ADS backgrounds, you find that this cohomology is graded by the R charge. And then actually you can then do localization. So another direction here is to calculate indices for the field theory by doing localization of gravity.
Okay, then let's keep it again.